Hello and welcome to Matrix Magic, Understanding Transformers with Matrices, Math, and Code. My name is Nada Tayeb. I'm a data scientist, and I build solutions for healthcare using generative AI. I was struggling to understand how transformers actually work. I, of course, read the papers, I listened to videos, I looked at the code, but it didn't click for me until I busted out an Excel spreadsheet, made some tables, and worked out the matrix transformations step by step. A painful process, but it finally clicked for me. So if you are on that same journey of trying to deeply understand how transformers actually work, then this might be the video for you. In this video, we are going to look at this diagram right here and go through it step by step. And at each step, we're going to look at the matrix transformations, the mathematical notation, and the PyTorch code. This talk is based on 3 key resources that I highly recommend. The original Attention All You Need paper from 2017, of course. The intuition, a great video called The Intuition Behind Self-Attention in Transformer Networks, and the seminal video, Let's Build GPT from Scratch in Code, spelled out by Andre Karpathy. All the code in this presentation is from his Colab notebook from that video, so highly recommend. Okay? Now, let's illustrate the difference between the encoder-decoder architecture versus a decoder-only architecture using a simple example like translating "how are you" from English to French. So first, the instruction and the sentence go in through the encoder through these inputs, right? Then it goes through some processing and then kind of comes in through here, through this multi-headed attention, and out pops the first word, comment, because that's the first word in how are you is comment. Now this output comes all the way back down here and starts processing through here. The word comment meets up with the original instructions, please translate how are you into French, and does some more processing, and out pops comment ça. Comment ça comes all the way down, goes back in, meets up with the instructions, and out pops va, and you have comment ça va, how are you in French. So you can see how for every word prediction, the original instructions get like a special attention and influence. Now, interestingly, many models like the OpenAI GPT models, ChatGPT, those are just decoder only models. They don't have this encoder part. All the instructions and the outputs are just fed in through here as a sequence. So please translate this "how are you" from English to French, goes in here and pops out comment. The instructions plus the word comment go back in and pops out ça, and so on, right? So we can output word predictions without even having a decoder. There are encoder-decoder models, decoder-only models, and encoder-only models. For the purpose of this video, we're just going to look at decoder-only models for simplicity. Because once you understand how this decoder-only model works, then it becomes easy to just plug an encoder in and understand how it works. Okay. So let's, with that bit of introduction, let's begin with the first step, which is to tokenize your training data. What does this mean? First, you have to get some training data. GPT was trained on the internet. We are going to train on 3 sentences. I like to eat soup. I am a good cook. Soup is yummy. In tokenization, you split your data into words and subwords, punctuation, and so on until you get a list of unique tokens which become your vocabulary. Here I have a vocabulary of 12 tokens. In contrast, GPT-3 has a vocabulary of over 50,000 tokens. But that would be hard to fit into a spreadsheet. Next up, now that we have our vocabulary of 12 tokens, we are going to initialize a token embeddings table. So In this step, each token is a row, and we can choose how many columns we want to use to represent each token. I chose 8 columns or dimensions. So D model equals 8 means there are 8 columns here. Okay. GPT in contrast uses over 12,000 columns here. The values can be initialized in different ways, randomly or with some pre-trained word embeddings or something else. So I just did it randomly just to keep things simple. And you can see here, as promised, I have, we are here in the output embeddings part of the diagram. And here you can see I've created, you can see the code where I've created an embeddings module and inputted 12 for the vocabulary size and 8 for the embedding size. Okay. Now, in our next step, we are going to pluck out the tokens for our batch. So we have to choose a batch and a block size that we want to train on. In this case, I chose I like to eat. I'm going to train the model on I like to eat and get it to learn what word should come next. Okay. Block size refers to the maximum number of tokens that can actually go into the model at any given time. You can have less than, here I chose 4, you can have less than 4, but the 4 is the maximum. And that actually relates to the concept of context window. So in GPT-4, you have a context window of 32,000 tokens, which means up to 32,000 tokens can be processed at any given time. And that's how it was trained as well. Okay, so we're going to pluck out I like to eat from that embeddings table that we just created. And now we have kind of our starting matrix. In the next step, we have to deal with this positional encodings concept because transformers, as you'll see, they don't have an inherent sense of the position of the data in the sequence. All the input tokens are processed simultaneously, as we'll see. And so the positional embeddings or encodings give information on the relative and absolute positions of the tokens within a text. And there are several ways to do this. The two kind of main ways are one, to just have a fixed formula. And that's what they have in that paper. And they have this alternating sine cosine function, right? So the first token, in position 0 will just be 0, 1, 0, 1, 0, 1. The second token will have these numbers using these alternating sine and cosine functions. So the model doesn't learn this, it's just fixed, right? It's a fixed formula. This is what's in the attention is all you need paper. However, Karpathy in his code used the position embeddings table. So just like our token embeddings, we can ask the model to learn position embeddings. And then these, and actually I should mention that any numbers in pink are learnable parameters by the model. So the model is going to learn this during the process. Okay. So in this step, you see this little plus sign in the diagram. That means we're going to add together the token embeddings and the position embeddings, which is as simple as just adding each, the corresponding cells together. So we're going to add 0.26 plus 0.42 will make 0.68 on this next table, and so on. And then you can see, maybe I can move my video a little bit. You can see this here. Token embeddings plus position embeddings. Okay. So next up, we're about to get to the attention mechanism. So actually I have to go back. How do I go back? Okay. So you can see now that we've done this part, we're about to head into the masked multi-head attention, and this is the crux of the video. But before we get there, we need to review something very important, which is, what are token embeddings? Well, what is an embedding? So embeddings are vectors that represent the meaning of the word. And the idea is that vectors of words or tokens with similar meanings are closer in space, like girl and boy in this example are close together, queen and king, sport and game, and so on. There is the best deep dive I found on the internet is this lecture from this Stanford course here. Highly recommend, because this is a concept that you need to get, right? But okay, so we have our vectors, they're numbers that represent the word, but there's kind of a problem, which is so many words have multiple meanings depending on their context, right? I swam across the river to get to the other bank. It's quite obvious to a human that bank in this case probably refers to a riverbank. I walked across the intersection to get to the other bank, probably a financial institution, probably not a blood bank, because it would be odd to have two blood banks right across from each other, unless maybe the whole article was about blood banks. But you can see we as humans, we can process that context and we know what kind of bank. But how do we tell that to an algorithm, right? Well, the solution is we take this. This is a really cool website where you can project a vector into three-dimensional space for a word and see what other words are close by. And you can see bank is really close to all these money words. But over here is we can see river and Thames, right? So if you want bank to mean riverbank, what you need to do is to kind of nudge this vector up and to the left a little bit, right? So how do we do that? How do we tell the model to pay more attention to the words like river and swam to tell us how to shift this word bank over so it'll be more river-like? That is where multi-headed attention comes in. Okay, and I know these look kind of scary. I'm going to show you the scale dot product attention and this multi-head attention diagram, but bear with me. You're going to get it in a few minutes, I promise. But before we go there, you see MAT-MUL, that stands for matrix multiplication. And if we really want to get this, we need to review some really basic linear algebra. And that is matrix multiplication and dot product. So in matrix multiplication, we're taking the dot product of these two vectors, the row vector here and the column vector here. And we're taking 1 times 7 plus 2 times 9 plus 3 times 11 equals 58. Then to get this number over here is 1 times 8 plus 2 times 10 plus 3 times 12 will get us this number here, and so on, right? That's a dot product. Now, the key concept that you need to understand is that one of them anyway, is that you have to know how a matrix, the shape of the matrix changes when you multiply two matrices together. You can see that for this sort of thing to work, the number of columns in this first matrix has to equal the number of rows in the second matrix, because otherwise, you won't be able to, you won't be able to match all of the numbers to get to this final dot product. And so you can see here, in matrix A has I rows and M columns. Matrix B has M rows and N columns, and see this and this have to match. Number of rows, number of columns match. And the output C has I rows and N columns, okay? So we end up with I and N in the final shape, okay? So just keep that in here for a minute. Okay. So now we are going to do some matrix multiplication. Do you remember that token embeddings plus position embeddings matrix that we added together and created? Well, now we are going to multiply that 3 times by 3 different matrices: the query's weights, the key's weights, and the value's weights. And look, these numbers are in pink, which means that the model is going to learn what those numbers should be. Those are parameters, okay? And we're going to, you can see there are 8 rows here, 8 columns here, and our output is going to be 4 columns and 4 rows. There you go. And here's the code. And this used to really confuse me, because you create a linear layer. The n embed is the number of columns you want to start with. And the second number, just call it head size, is the number of columns you want to end up with. But what's going on in the middle? What's going on there? What's going on there is, in the background, this weight matrix is being created, right? That's the magic. And here's another diagram that you see a lot when you're learning about deep learning. And there are these neurons. Two neurons are connected, and they create this hidden layer of three neurons, and you output two neurons. What the heck's going on? Well, what's going on here is matrix multiplication. Here is a matrix with however many rows, 4 rows, 50,000 rows, doesn't matter, but it has two columns. And over here, I want a matrix with the same number of rows, but 3 columns. I want to stretch it out. So to do that in the background, this weights matrix, that's what's going on here, okay? A weight matrix with 2 rows to match the 2 columns here, and 3 columns to match the output you want. So all that's happening in these linear layers is that you're smushing down matrices or stretching them out, or maybe even keeping them the same size, okay? By multiplying the original matrix by a weight matrix. Okay, so that's the magic that's going on all through this transformer. Okay, so remember our queries and keys matrices that we created these 3 matrices, right? Queries, keys, and values. And we're going to take queries and multiply it by the transpose of the keys matrix. And transpose means we just switch around the rows and the columns, okay, to get this attention matrix. Okay, and so here's the code: Q, matrix multiplication, K, transpose, and that's just messing around with the dimensions a little bit. And so here we are, we're at this first matrix multiplication, and we're in the scale dot product attention part of the diagram. Okay, hope you're still with me. Now we're on the next step. This is an easy step, with just taking Q times K transpose, which we just did, and we're dividing it by the square root of dk, which is dimensions of the keys matrix, equals the number of columns in the keys matrix, okay? And which is 4, so that's easy, by the square root of 4. And why do we do this? Because later on, we're going to apply something called softmax, okay? Which takes numbers and converts them into probabilities. That's pretty convenient. However, if you have large values, the softmax will start paying too much attention to only the word with the largest numbers. It's called softmax saturation, not good. So to reduce numerical instability during the optimization of the learning phase of training this model, you want to scale the numbers. So you're going to scale the Q times KT. Okay. But whatever it is, this is an easy step. We're just dividing everything by the square root of dk, which in this case is 4, okay? And there you have it over here in the map. We're in the scale part of this diagram. We're still up here in this purple box of the multi-headed attention diagram. And here's the code. Weight times C, that's 4. And it's, 1 over the square root. Now we have scaled attention. Okay, next up, masking. Now remember, in a decoder only model, like the word I just gets to see itself. It doesn't know about the other words. The word like only knows about the word behind it. The word eat knows about all 3 words behind it. Okay, so we don't want to, when we're training the model, we don't want to give it information that it wouldn't have in the real world when it's trying to predict what word comes next. And therefore, we have to fill in the top half of this triangle with zeros, okay, or actually negative infinities, so that they can't, so that the future can't influence the past in a sense. And I'll show you that in a second. So here we are at the softmax stage, where we're going to take the, we're just doing this formula. We're taking the exponential of each element, and then adding them up, and then dividing the exponential of each element by, the sum across the row, and voila, magically, now our numbers have been converted into probabilities. And sure enough, the word I, 100% of the probability is just on the word I. There's not, it doesn't know about the other words, it just only knows about itself. So the other words here are just zeroed out. Whereas the word eat, it can pay attention to any of the words in its past, but in our toy example, it's just decided that the word I isn't too important. I'll move myself up here. Here's the code. You could just call a softmax, throw in the weights, and it kind of does it for you. No big deal. Okay. Okay, now this is where things get really, really interesting. So bear with me here. We're this final matrix multiplication, where we're going to take our masked attention multiplied by the values matrix. Okay, and here you can really see what's going on. Remember, when we're doing matrix multiplication, we're going to take this row and multiply it by this column. And to get this this value right here, right? So as you can see, the the D1 for the word I, it is we're going to take all of its original number 1.73. Right? This is its original vector, right? And the original value here is 1.73 and multiply it by 1. Okay. And then none of these other words, right, D1 for like, to, and eat, they're all just zeroed out, right? They don't get to have any say in what's going on, right? So we're just going to be left with 1.73. And you can see that the vector I has not been impacted at all. It's exactly the same as it was before because there's no prior context to impact the word I. However, the word eat is different. Here, we're going to take this row right here, and we're going to multiply it by this column right here. So in my toy example, it's saying, okay, give 0 weight to the word I, give a little bit of the word weight to the word like, a little bit of weight to the word to, and most of it to the word eat. Again, toy example. But you can see now that this 4.18 has been changed slightly. Now it's 4.13, right? And this entire vector here for the word eat has now been slightly changed. It's like all the other words that preceded it got to have a little bit of a say in the new vector for the word eat. And how much of a say? Well, that depends on the attention matrix, which is saying pay more attention to these words and less attention to these other words. So if this was working in a real model, it would basically say for I swam across the river to the other bank. Hopefully, the word bank would be heavily impacted by the word swim and river. Okay, so that's what's going on. And now we have this new vector of weighted values. Okay, we've reached to the top up here, and we've completed this formula. A softmax of Q times the transpose of K divided by the square root of the dimensions of K times this values matrix gets us to our attention, our weighted values. Okay. And I just put the math in here for this 4.13 if you want to check it out. Okay, so we don't just do attention one time. It's called multi-headed attention because can do it n times. And the idea behind that is if you have lots of attention mechanisms going on in parallel, then each attention matrix can learn something a little bit different, right, about the language. In this step, I just decided to have, why not, 4 attention heads. In this step, we just concatenate them together. So we take all 4 matrices and just create one giant matrix of 16 columns, okay? And here is the code right here. We just concatenate, and here's the math right here. We're going to concatenate them all together. And then see this weights here? Well, that is this final linear layer. So let's go have a look at that. And if you, again, here are pink numbers. This is a learnable parameter. We're going to take our, the 16, and we are the matrix of 16 columns, and we're going to shrink it down to 8 columns. By multiplying it by these parameters, this table has 16 rows and 8 columns. So you see, it's just that that same, just another matrix transformation once again. And here you have it, this linear layer right here. Um, I will explain what dropout is later. In the original paper, it doesn't have the dropout layers, but in Karpathy's code, he does. So it's worth mentioning. Now we've gotten through all of the masked multi-headed attention. This is fantastic. And we are at addition and normalization. Okay, we went through so much trouble to kind of massage our vectors this way and that way based on their context. Now we're just going to add back that original token embedding plus position embedding table and just smush them together to get a new matrix. So the reason that we do this is because it makes it easier in the training process. And Kaparthi has a really great explanation of this. If it just give me a second. So it's called a residual connection. And the main purpose of this step is to help allow information to flow more easily through the network during backpropagation. Again, Karpathy's video is a really great explanation. So I'm just going to leave it at that for the purpose of this video. And then over here, you can see the code, that original X here, this matrix plus, this multi-headed attention, this whole business that we've done with the linear layer, and we've just added them together. That's it. Next up is this layer normalization. Put myself up here. So this operates on the columns of a single row, and it's going to change this row of numbers into some new numbers wherein the mean will be 0 and the variance 1. And in the PyTorch implementation, there's also an error term and some other learnable weights. But for our spreadsheet purposes, we're just going to not bother with the learnable weights. Normalization helps improve training and performance in a number of ways. And you will just sort of leave it at that for the purpose of this video, but you can certainly read more about that. And here, our spreadsheet, I got the mean, I got the standard deviation, and just calculated it out. So fairly simple, right? And here it is in the code. You just call layer normalization, and it does it for you, and done. No big deal. Now we are getting to the feed-forward network, right? And the feed-forward network really has 4 parts to it: a linear layer, a ReLU, another linear layer, and the dropout, which we'll talk about. So let's go. Okay. Once again, we're starting with a matrix with 8 columns. We're going to stretch it out to 32 columns by multiplying this learnable weight matrix. And here's the code down there. We started with 8, going up to 32. And this kind of happening backstage. ReLU is interesting. It's just a fancy way of saying set all your negative numbers to 0, okay? And keep positive numbers the way they are, okay? It's pretty easy. It's called rectified linear units, ReLU. Negative numbers go to 0. That's all you really need to know here. This linear layer, we're taking the 32 and smushing it back down to 8 columns by multiplying this matrix by this learnable weights matrix, okay? And here you see again the code. We go from 32 down to 8, because remember, n embed is 8. In dropout, during training, we randomly set some of these values here, these neurons, to 0 during each training pass. This does not occur during inference. And we do this to prevent overfitting. Overfittings where a model learns a particular data set really well, but doesn't do a great job of generalizing to other data it hasn't seen. And so it's kind of like you want to make it just sort of make it a little bit harder for the model to learn so that it's able to generalize better, kind of. So that's what dropout is. And here you go. Let's put it all together. We have our ReLU. We stretched out the matrix. we set the negative numbers to 0, we smushed it back down, and we performed dropout. And here we are, feed forward. The next step is another round of addition and normalization. And we've already covered that, so I won't go over it again. Instead, let's skip to the really exciting part where we're getting closer to actually the crux of it. The entire goal is we want to predict what word comes after eat. So how are we going to do that? Well, first of all, we need to get our matrix back to the right size. We need to take it from our embedding size of 8, to kind of help with the look of the code here, to our original vocab size of 12. Okay, so we apply another linear layer, have this weight matrix here, which is able to transform this matrix of 8 columns to one with 12 columns. And then, if you recall softmax is going to take our logits, our numbers, and convert them into probabilities. Okay? So now we have probabilities. So every row sums to 1, right? It's telling you, here's the word eat. And now we can look at this. We're saying we can look at this row and predict, based on our toy example, of course, what word has the highest probability of coming after eat if eat has been preceded by I like to. And that word is good. Okay. There are also other ways of doing this where instead of just picking the highest probability word, we sample from a distribution. So, there's a little bit more variability in what gets picked and, all kinds of fancy ways to do this. But in this case, we're going to just look at the highest probability word, and that word is good. So we went through all this entire exercise just to get to the word good. And what's really interesting is that's happening over and over again. I like to eat good, or to like to eat good, because we can, in our toy example, we could say, we only have a context window of 4. That will go back through this again to try to output the next word and the next word and the next word. So it's this entire sequence just keeps sort of cycling through this giant math equation to keep predicting what word comes next. But that isn't actually the end of the story, because we didn't talk about what NX means, right? We talked about output embeddings, right? You get we're training a model. We get our vocabulary, we turn it into tokens, we take out our first batch, like I like to eat, we pluck out the word vectors, the output embeddings for those tokens. Then we add on the positional encoding. Then in this box here, we're doing the masked multi-head attention with the QKV and multiplying them together and so on. We're doing this addition normalization step. Don't worry about this just yet. We're doing feed forward, addition normalization, so on, and finally getting out our probabilities. And you see this right here is a layer. This layer can take place n times. So we do this once, and instead of going here to linear and softmax, we just feed it in again. And we can do it again and again and again, n times. Okay? And now that you've understand how mass multi-head attention works here, we can now understand what's happening with this encoder. What's happening here is instead of just having those original instructions just keep feeding through as a sequence, if you remember, the instructions like, please translate how are you into French, goes in through here, does its own attention thing, and spits out a matrix. And that matrix becomes the Q and the K of this multi-head attention step. This is called cross attention. So it's like those instructions now get to have special influence on the word vectors that are coming in through here, that have been inputted through here. All right, so that is the concept of cross attention. And you think that would always be the better way, but amazingly, the GPT models do so well with just a decoder only model. So there you go. There are a lot of just plain decoder only models out there. And actually here you can see some, right? Here, decoder only models, encoder decoder models like T5 and BART, and encoder only models like all the BERT based models. And if you've been doing NLP for a while, these are the types of models that I used to work with until generative AI kind of exploded onto the scene, really, I guess, really last December. Now, this is what I really find amazing. Now that you really more deeply understand what these terms mean, let's just sort of absorb the scale of even a model like GPT-3, right? Because GPT-4 is got to keep their stuff secret, but let's look at GPT-3. Remember all those pink numbers that are learnable parameters? I said the model's going to learn those. Well, there are also other parameters, but those really make up the bulk, right? Those in those weight matrices. There are 175 billion of those in the GPT-3 model. 175 billion were trained and are stored. Instead of one layer, right, there are 96 layers. So that whole uh, attention and the feed forward network and so on, and that took place 96 times in sequence. RD model was eight. We had 8 columns, right, in our embeddings, original embeddings. GPT-3 is 12,288. I used 4 attention heads in my toy example. GPT-3 is 96 attention heads. I had 4 columns in each attention head. GPT-3 is 128 columns. I did one batch. GPT trained with 3.2 million batches, a batch size of 3.2 million at a time. Learning rate here refers to how quickly the model weights are updated during backpropagation. So the lower the learning rate, the slower the learning takes place, but presumably the more accurately it learns. And so you can see that number has been going down with each iteration of GPT-3. So now if you wonder why, these large language models are so expensive and so slow, I hope this helps to put some of that into perspective. Okay. So I hope you have enjoyed this journey and that you now have a deeper understanding of how transformers work and the matrix match behind them that really is changing our world, right? And I also here are some high resources that I highly recommend. Thank you for listening and good luck on your learning journey. Bye.